Let's see 8 examples on how to use the direct comparison test or the limit comparison test to see if a series converges or not. This is the first one. Series as n goes from 1 to infinity of 1 over n plus 2 to the n. Let me write this down again. This right here is not so bad because we only have 1 on the top and 2 terms on the bottom. Pick up the dominating part, which in this case, it will be 2 to the n, because 2 to the n is so much bigger compared to n, as n goes to infinity. So let's just look at the series as n goes from 1 to infinity of 1 over 2 to the n. Well, n is positive because n goes from 1 to infinity. Both of them have 1 on the top. We are adding n right here. So the denominator here is bigger than this denominator. But when we have 1 over this compared with 1 over that, the whole thing is less than this right here. Just a quick example. We know 5 is bigger than 3. But today, if we have 1 over 5 and then 1 over 3, which one is bigger now? This right here is actually bigger, right? Same thing. 1 on the top. The smaller the denominator, the bigger the whole thing is. And I would also like to put down a equal sign, even though it's strictly less than, but if you just have the equal sign here, that's okay too. Now, let's observe this. This right here is really just the series as n goes from 1 to infinity of 1 over 2 to the nth power. Have a look. This inside is just a what? A constant. So in fact, this to the nth power, we can say that it's a geometric series. Common ratio is 1/2, and the absolute value of the common ratio is less than 1. Therefore, this right here converges. And now we have shown that this is less than or equal to a convergent series. And by the way though, 1 is positive, n is positive, 2 to the n is also positive, and we're just adding everything up. So for sure, this right here is non-negative. So with all that being said, we can conclude that this right here also converges. It has to be a smaller finite value and cannot get to negative infinity because we mentioned that this is non-negative. So now we can come here and say this right here converges by, because we use the inequality, so it's the direct comparison test. Now, just some small remark. What if we use 1 over n series earlier? Have a look. If you compare the series as n goes from 1 to infinity of 1 over n plus 2 to the n, and the series as n goes from 1 to infinity of 1 over n, this is still going to be less than or equal to this one because here we are removing this positive part. So still, this will be smaller than that. But now, this right here is actually a what? It's a harmonic series that diverges. This is a divergent harmonic series. Well, you can look at the P. This is a P series, right? P is equal to 1. And it diverges to infinity. But this right here, this inequality to us is not helping because what? This right here, when you have less than or equal to infinity, this could be a smaller infinity or it could be finite. We don't know. We cannot draw any conclusion right here. We cannot say this right here also diverge because the truth is this right here actually converges. We cannot say this right here converges because it's not guaranteed. It could have been a smaller infinity. So don't do this. Even though this is true inequality, but it is not helping. So let me erase that. This right here, it's the first one. And now we have more to come. Here, let's go ahead and go over number 2. Here we have the series as n goes from 1 to infinity, 3 to the n over 2 to the n plus 4 to the n. Again, let's pick up the dominating part. Here, let me write this down. Well, on the top is just 3 to the n, so we still have to have that. And on the bottom though, which one is bigger? Well, this right here is going to be bigger, right? So that's the dominating part. So 4 to the n. Well, here again, just like what we had earlier, the numerator is the same. On the bottom here, 2 to the n is always positive. When you take that away, this whole thing is going to be less than, and that's also put on equal to, less than or equal to that. And now if you observe this, this is just the series, n goes from 1 to infinity. We can put the n on the outside, so we have 3 over 4 raised to the nth power. Aha! This right here, it's another convergent geometry series because the absolute value of this is indeed less than 1. So this right here converges. So we can come here and say this right here also converges. And perhaps that's also mentioned that this right here is non-negative. Again, do not pick 3 to the n over 2 to the n, otherwise you'll run into a similar issue that we mentioned earlier. So for number 2, this right here converges by inequality here, so it's the direct comparison test. Now for number 3, series as n goes from 3 to infinity of ln n over n. Let me write this down again. So what do we compare though? Notice on the bottom we just have n to the first power. So imagine if you have the series as n goes from 3 to infinity of 1 over n to the first power. You see how I just kind of ignore the ln n? This right here is a divergent harmonic series. And now check this out. This, because on the top we have ln n, but here we have just 1. And the truth is, ln n is indeed bigger than or equal to 1, as n is greater than or equal to 3, right? 3 to infinity. So perhaps right here I will just mention that we know ln n is greater than or equal to 1. So this inequality holds. And I'll just say that ln n is greater than or equal to 1 for n bigger than or equal to 3. Now, this right here is a divergent harmonic series that goes to infinity. You can also mention that this is the divergent P series, but I will just say that the harmonic series right here, harmonic series. It's just a special name for it. Technically, not the whole thing, but we are missing like a few terms in the front, right? This is 1 over 3 plus 1 over 4 and so on, but it will still go to infinity anyway. That's okay. Now we have this is greater than or equal to positive infinity. So what can we say? We can say this right here must also diverge to a bigger infinity. But we can just say this right here also diverges thanks to greater than infinity. So right here we can say that is a divergent series by, again, direct comparison test. Now for number 4, notice that we have n plus 2 over n to the third power plus 4. So if you want to use inequalities, it might not be the best. Sometimes it still works, right? Now for number 4, we have the series as n goes from 1 to infinity of n plus 2 over n to the third power plus 4. In such situation, if you want to use inequalities, it might not be easy sometimes because it's not clear to see. You cannot just remove a number from the top and remove from the bottom and then set an inequality. That's not always true. For example, if you have, let's say, 1 plus 1 and then over 2 plus 2. If I remove this and that, yeah, what can I say about this and this? In fact, they are equal. Right? If you remove this and that, in fact, they are equal because this is 2 over 4 and this right here is 1 over 2. So when you are adding a number or subtracting a number both to the top and to the bottom, inequalities, you have to be careful. Sometimes you can set it up and then cross multiply, that's okay. But in this case, remember we still have the limit comparison test. Let's try this right here. compare the dominating part. On the top it's just this, on the bottom it's just that. So in this case, if we focus on the series as n goes from 1 to infinity of n over n to the third power, we can reduce that. It's just going to be series as n goes from 1 to infinity, 1 over n squared. Have a look. Here, it's a p-series where p is equal to 2 and p is greater than 1. Therefore, this series converges. Now, what we have to do is to check the limit. This is a limit comparison test. It's easier sometimes with like fraction situation. So what we do is just check the limit as n goes to infinity. Let's put down just the formula part right here. So it's n plus 2 over n to the third power plus 4 over this right here, which is simplified into that. Now, let's just compute the limit. For this right here, we can just multiply the top and bottom by n squared, so that this and that cancel, and we get the limit as n goes to infinity of distribute, right? Because technically there's like invisible parentheses. Distribute, we get n to the third power plus 2n squared. On the bottom is just still n to the third power plus 4. As n goes to infinity, again, just compare the dominating parts. Here, it's the highest power of n, which is just n to the third power. Here, it's also n to the third power. Reduce to get 1. The limit for this right here is just equal to 1. And if your teacher would like you to divide all the terms by the highest power, just go ahead and do that. So divide everybody by n to the third power and then show this and that goes to 0. But I think this right here is pretty clear. Now, we are trying to use the limit comparison test. Yeah? When we end up with 1, we just have to mention that this right here is positive and not equal to infinity. The idea behind this is that this ratio, the ratio of this and that, is equal to 1. So they are pretty much about the same size. In another word, this series and that series, it's pretty much the same size. The ratio is about equal to 1. So, because we know that one right here converges, so we can come here and say, this right here also converges by limit comparison test. Now, next one, we have the series as n goes from 1 to infinity of sine of 1 over n. For this one, because we're dealing with sine functions, I don't think inequality works out nicely, right? But if we look here inside, we have 1 over n. So let's try the limit comparison test. But let's go ahead and write down what we know first. If we are just focusing on the series as n goes from 1 to infinity of 1 over n, let's call this as the p series. This is n equals 1. So p is equal to 1, which is less than or equal to 1. Therefore, this series diverges. We can also call the harmonic series diverges. Here, let's go ahead and check. Let's use limit. Check the limit as n goes to infinity. This is the one that we're trying to get, and just write down the formula part right here, which is sine of 1 over n. And then let's put down this right here, 1 over n. Okay, as n goes to infinity, notice this and that, they both go to 0. This is a 0 over 0 situation. Do not use L'Hopital's rule though, because this is a special limit. What we are going to do is, we're just going to say, let theta, the input here, is 1 over n. So as n goes to infinity, we know that theta will go to, we put infinity to here, 1 over infinity is 0. So we have the limit as theta goes to 0 after the substitution. Here we get sine of the input, which is theta, and the bottom is also theta. This is the limit. You know the answer for this is equal to 1. Again, this right here, after the limit comparison test, make sure that it is non-zero, right? It's finite, so it has to be greater than 0, and it cannot be equal to infinity. Therefore, we get to draw our conclusion. This right here also, when you are using comparison test, make sure you have the word also in your mind somewhere, because you don't want to do all the work and then you put down this right here converges. No. When you put down the word also, you can look what you put down earlier. Also diverges. That's how you draw the connection. That's why it's called comparison. Also diverges, and we say that's because of the limit comparison test. Now, what if we have the series as n goes from 1 to infinity of sine squared, and then here inside is 1 over n. Here, earlier, we used the series of 1 over n, but here we have sine squared, meaning sine times sine. So in fact, for this one, we are going to use the series as n goes from 1 to infinity of 1 over n squared, and you'll see why. Here, it's a convergent p series because p is equal to 2, which is greater than 1, so this right here converges. Now, again, check the limit. So we check the limit as n goes to infinity. That's the one we're trying to do, so sine square of 1 over n. And we put down this right here that we know. Alright, before we do the substitution like what we did earlier, let me split this. This right here is the same as the limit as n goes to infinity of, this is sine of 1 over n times another sine of 1 over n. Haha. On the bottom, also do the same. 1 over n times 1 over n. So imagine earlier, if you only put down 1 over n to the first power. In fact, this right here, if you work that out, the limit you will get is going to be 0 or maybe infinity. It's not going to work out to be a finite value. And if you have 1 over n, it won't help you to draw conclusion. But this right here will, because now we can do exactly what we did. Let theta equals 1 over n. As n goes to infinity, we know theta will be going to 0. Here, the limit of a product, it's a product of the limit. So we can look at it like this. The limit as theta going to 0, and let's write down sine theta over theta, and then times limit of the other right here. Over theta. But at the very end, we are just really doing 1 times 1, which is still equal to 1. And same conclusion like earlier. It's greater than 0 and not equal to infinity. You have to make sure that the limit that we get right here after the limit comparison test is a positive finite number in order for us to draw a conclusion. Try it if you have the series as 1 over n to the first power, then this right here, you'll just have 1 over n. Yeah, so you have 1, and then you end up with 1 times 0. It's not going to help. Yeah. But anyway though, this right here, we can come here and say this also, what now? Converges. Also converges by limit comparison test. Now, number 7. This time we have the series as n goes from 1 to infinity, and then we have 2 terms on the top, n plus 1, and the bottom here is square root of n to the third power. You can do either the limit comparison test or the direct comparison test. In my opinion, direct comparison test is nicer, so I will show you that. So here we have this series, n plus 1 over square root of n to the third power. This time though, we have two terms on the top. I'm going to ignore the plus 1, right? Again, pick out the dominating part. So we are looking at this compared with the series n goes from 1 to infinity of n over square root. Let's write it as 1/2 power already. So it will be n to the 3 over 2 power, like this. Now, this time we are removing a 1 on the numerator. So this right here will actually be bigger, and again put on equal to, than this one right here. All right. Now if you work this out, this right here is the series as n goes from 1 to infinity. This is n to the first power, and just do 1 minus 3 over 2. And we will end up with negative 1/2. And that will be the new exponent, which will give us 1 over n to the 1/2 power on the bottom, right here. So now, for this series, we know that it's a p series, and p is equal to 1/2, which is less than or equal to 1. So what's the conclusion for this? This right here is what? Divergent p series. And we have successfully shown that this series is greater than or equal to a divergent series, and we know this right here diverges to infinity. So here, this right here also diverges. So we can say this right here diverges by, here we are doing the direct comparison test. Done. Because we are using inequality. Now, last question. This right here looks like a series that is calling out for us to use the limit comparison test, because of course I don't want to deal with inequality in such a situation. So let's go ahead and pick up the dominating part and see what it tells us. This is a series that we will know much better if we look at the series as n goes from 1 to infinity, n to the second over n to the fifth, which reduces to 1 over n to the third power. And then we can see that the p here is 3, which is greater than 1. Therefore, this series converges. Yes, when we are doing comparison test, definitely think of the p series and the geometry series a lot. But sometimes there may be different series that you can use to compare as well though. Anyway though, here we are going to check the limit. So we check the limit as n goes to infinity. Let's write down this right here on the top, n squared plus 3 over n to the fifth plus 4n plus 1. And let's put down this on the bottom. Now I'm just going to flip this, just multiply n to the third power here and here. So we are looking at the series, no, we're looking at the limit as n goes to infinity. Distribute this to the top. So this is n to the fifth plus 3n to the third, and the bottom is n to the fifth plus 4n plus 1. And when we have such situation, just compare this and that, because n goes to infinity. Reduce to 1, and that's the limit, and the limit right here is positive, and it's not infinity. Therefore, we can compare and say this right here. I haven't used the word also, so let's go ahead and put that down. Also what? Also converges. Why? By limit comparison test, LCT. And now you know how to use the direct comparison test or the limit comparison test. Best of luck in your Calculus 2 class. That's it.